Hey everyone, and welcome. Today, we're diving into the world of coordination compounds. And trust me, this is cool stuff. Think of them like a chemical construction kit, tiny, intricate structures that are behind everything from the color of a sapphire to the way your body uses oxygen. So let's get building. So, you ever look at a chemical formula and think, something's not adding up? You see the atoms, but the way the compound actually behaves just doesn't seem to fit. There's something else going on, a secret in their structure. And that's exactly what we're going to unlock today. And here's how we're going to do it. First, we'll tackle that chemical mystery. Then, we'll learn how to build one of these complexes piece by piece. After that, we'll crack the code for naming them, understand the science behind their bonds, explore their incredible properties, and finally, see just how these little compounds really do change the world. All right, section 1. Let's kick things off by digging right into this chemical mystery. It's time to find out what makes these compounds so special. So what's the big secret? Well, it's this: the coordination compound. This isn't your everyday molecule. At its heart, you've got a central metal ion, kind of like a hub, and attached directly to it are a bunch of other molecules or ions that we call ligands. This unique core plus attachment structure is the key to everything. Okay, now for the really fun part. To truly get a handle on this, we're not just going to talk about it, we're going to build one from scratch. Think of it like a chemical Lego set. Let's break down the anatomy. Every great build needs a foundation, right? For us, that's the central metal ion. It's usually a transition metal, like this iron ion here. Its job is simple but crucial. It sits right in the middle and acts as an anchor, ready to accept pairs of electrons. So if the metal is the anchor, what attaches to it? These are our building blocks, the ligands. These guys, like this cyanide ion, have a spare pair of electrons that they're ready to donate, forming a special kind of bond with that central metal ion. Now, not all ligands are created equal. Some are simple, they attach at just one point, we call them monodentate, but others are way more complex. You've got bidentate and polydentate ligands that act more like grappling hooks. They can grab onto that central metal in two or even multiple places at once, and trust me, that's going to be super important later on. So what do you get when you snap all those pieces together? You get what's called the coordination sphere. It's the central ion and all its attached ligands, all bundled up. You can always spot it in a formula because we wrap it in these square brackets. This is the main event, the functional heart of the compound. But wait, look at this sphere we just built. It's got a charge of -4. We can't just leave it like that. That's where the counter ion comes in. In this case, we have 4 potassium ions hanging out outside the sphere. Their only job? Balance the books, electrically speaking, and make the whole compound neutral. And just like that, we've built a complete coordination compound. So we've built this awesome, complex thing, but what do we call it? How do we give it a name so that any chemist anywhere in the world knows exactly what we're talking about? For that, we need to open the instruction manual, the official iupac naming rules. Now, I know this looks like a lot, but honestly, it's a beautifully logical system. You just follow the steps. You start with any ions outside the sphere, then you name the ligands inside alphabetically, using prefixes to say how many there are. Then you name the metal with its charge in Roman numerals. And one last little twist, if the whole sphere is negative, the metal's name gets an 8 ending. That's it. Let's try one out. For this compound here, we start with the counter ion on the outside, chloride. Easy. Then we move inside the brackets. We have 6, that's hexa, ammonia ligands, which in this system we call amine. The metal is chromium, and a quick calculation tells us its charge is +3, so that's chromium IV. Put it all together? Hexaamine chromium IV chloride. See? Follow the recipe and it just clicks into place. Okay, we know what they are and we know how to name them, but why do they form these particular structures? What's really going on with the electrons that holds them all together? To answer that, we need to take a quick peek at the major theories that explain the bonding. Think of it like this. Our understanding got better and better over time. First, Werner's theory gave us the basic idea of the structure. Then, valence bond theory came along and used the concept of hybrid orbitals to start predicting their shapes. And more recently, crystal field theory gave us this amazing way to explain their magnetism and, my favorite part, their incredible colors. Each theory adds another layer of detail to the story. All right, so we've built it, we've got the theories, now let's talk about the cool stuff, the consequences. Because of this unique structure, coordination compounds have some truly fascinating properties, from their 3D shapes and their stability to those vibrant colors we just mentioned. And this is where it gets really mind-bending. You can have the exact same chemical parts, the same formula, but arrange them differently in space. We call this isomerism. A common example is cis and trans. Cis means two identical ligands are neighbors, side by side. Trans means they're on opposite sides, kitty corner from each other. Same parts, totally different molecule. And you might be thinking, so what? A different shape? Big deal? Well, it is a huge deal. It can literally be a matter of life and death. Take cisplatin. This amazing cis isomer is a powerful anti-cancer drug because its specific shape lets it mess with cancer cell DNA. But its identical twin, transplantin, same exact atoms, just in the trans arrangement, is completely useless as a cancer treatment. Shape is everything. Hey, remember those grappling hook ligands we talked about? The ones that can grab on in multiple places? This is where they really shine. It leads to something called the chelate effect. Basically, a molecule that's holding on with two or more hands is way harder to break apart than one holding on with just one. This effect creates incredibly stable compounds, which is a massive advantage in all sorts of applications. And what about the colors? Why are so many of these compounds just so beautiful and vibrant? Well, that brings us back to crystal field theory. The ligands actually cause the metal's d orbitals to split into different energy levels. So when light shines on the compound, an electron can absorb the energy from one color, let's say orange light, to jump up to a higher level. What our eyes see is the color that's left over, in this case, blue. And that little jump is called a d-d transition. So this isn't just some neat thing that happens in a chemistry lab. We've seen the theory and the properties, but the real story is that these compounds are absolutely everywhere, doing some of the most critical jobs in nature, in medicine, and in industry. You literally wouldn't be alive without them. The hemoglobin carrying oxygen through your veins right now, that's an iron coordination compound. Chlorophyll, the molecule that lets plants eat sunlight, that's a magnesium complex. Even vitamin B12 is an incredibly intricate cobalt complex. They are the essential machinery of life itself. And it doesn't stop with biology. We've taken this idea and run with it. We've already talked about the life-saving drug cisplatin, and that super stable ligand EDTA. We use its chelate effect to literally snatch the minerals out of hard water, making it soft. There are also absolutely vital tools in chemistry labs for analyzing and identifying metals. So we've gone from a simple puzzle about a chemical formula all the way to the machinery of life and medicine. Nature uses this chemistry to capture sunlight and carry oxygen. We use it to cure disease and purify our water. It really makes you stop and wonder. With this incredible chemical construction kit at our fingertips, what amazing new things will we be able to build next?